So, it's 2 p.m. and it's time to start today's event. So I would like to welcome everybody to this doctoral thesis defense, and I would especially like to welcome the doctoral candidate, Ulrik Dam Nielsen, and the two official opponents, Dr. Bas Buchner, President at the Maritime Research Institute Netherlands, and Professor Attila Indricic, the Associate Principal and Executive Dean of the Faculty of Engineering and a Professor of Offshore Engineering at the University of Strathclyde. Also a welcome to Professor Harry Bingham from the Department of Mechanical Engineering at DTU. He is the chairman of the assessment committee. My name is Rasmus Larsen. I'm the provost and chief academic officer of this university, and today I'll be the chairman of the proceedings. We have a doctoral thesis entitled Sea State Estimation Based on Measurement of Wave-Induced Ship Responses that was handed in to the Technical University of Denmark. Following that, after the acceptance from the department, an assessment committee was appointed, and following the assessment committee's positive response on accepting the thesis for defense, we have scheduled today's event. The proceedings of this afternoon will be as follows. So after my small introduction here, I'll invite the doctoral candidate to the podium to give a presentation of his work in a lecture of approximately half an hour. And after that, we'll have a small break to rearrange for the question and answer session of the event. The opponents will, in turn, discuss the thesis with the candidate. After that, there will be the possibility of questions to the thesis from the auditorium. And if there are any opponents in the auditorium, please register with me in the small break after the lecture. After that, the official part of the doctoral defense is over, and DTU will host a small reception in the lobby just outside the auditorium, and I hope you will all be able to join us there. Now, this thesis is concerned with efficient and safe marine operations in the light of conditions at sea, specifically the sea state. And this is, I think, a particularly fitting topic for research in a nation like Denmark, with a very long tradition for marine operations, whether it's shipbuilding, shipping overseas or internal waters, in fisheries, in operation of large offshore installations for oil exploration or for wind power production. Our society relies on efficient and energy efficient and safe operations, and this work, I'm sure, will, and maybe it's already had, a contribution to this. DTU itself is actually also a ship owner. We have, if not a fleet, then certainly a large one-digit number of vessels in operation, ranging from rigid hull inflatable boats to ferries, a ferry servicing an island, steel hull fishing boats, and our crown jewel, Dana, a versatile, multi-purpose research ship capable of worldwide operations, including ice navigation. Now, this ship has been in service for 40 years and is due for replacement, and a decision for this is due in the Danish government, and DTU's opinion is that it's crucial for Denmark that we have such a research vessel that can fulfill our obligations for fisheries monitoring in the North Atlantic, and to have the necessary research capability to operate in the North Atlantic and in Arctic waters, not the least in the light of the changing conditions in the North Atlantic with respect to sea traffic and fisheries that are due to the climate change in these areas. We think that it's important that Denmark stays ahead and that we can support also industrial development in that region and to be on the geopolitical scene and contribute to a manifest position as an Arctic nation. In the same way that the work presented here today, in the long term, will contribute to Denmark retaining a role in marine operations locally and globally. So with these words, I would end my introduction and invite Ulrik Dam Nielsen to the podium to present his work on sea state estimation.
Thank you very much, Rasmus, and also for giving the introduction and the motivation to hold my whole study, so it's already in place. Now, welcome everyone, in particular to the assessment committee. I look forward to some discussions. So the topic of today is sea state estimation based on measurements of wave-induced ship responses. So before I dig into it, what I'll present to you today is, you can say, a fairly non-technical overview of my work on this topic during the past 12 to 15 years. I think one of the reasons why I find this topic fascinating is that it has elements from many engineering disciplines, sub-disciplines. You can name naval architecture, seakeeping, time series analysis, control theory, fault diagnosis. So it really covers a broad spectrum of engineering disciplines. And then, of course, I think this topic, the use of ships as wave buoys, has many unexplored practical applications. And with this, a short outline of my talk today. I'll introduce a little more than Rasmus did, and I'll talk about this concept, the wave buoy analogy, and I'll mention some of the interrelated studies that have been included as part of my work on this overall topic. And finally, I'll conclude and bring my view on the future. So, in the first place, why do we actually want to measure waves, estimate waves? In my case, it's very much concerned about ensuring safe, green, and efficient marine operations. This goes for ships in transit, especially in adverse weather. Could be related to crane and tow operations during installation and maintenance of wind farms and fish cages. Vessel performance monitoring, especially related to the estimation of the added wave resistance that has become you can say, a popular topic in the recent years. And also, I think it has values to be a kind of a black box on a ship, somewhat similar to what we see on airplanes. So, in case of any accidents or other smaller incidents, you could look up what was actually the exact wave conditions if you continuously was monitoring using this principle. And what I'm not dealing with in my own field of research is climate changes as such, but some of the colleagues are, and I think also in this perspective, the measuring of waves is important in order to understand the mechanism of surface water mixing and air-sea fluxes. But I've covered in my topics of today, and in the thesis, it's the upper elements. So if we should talk about some well-known means for sea state estimation, we have the classical wave rider buoys. We can do remote sensing using aircraft or satellite. It could be based on the navigational radar used as a wave radar. All of these means have their own pros and cons. What we should keep in mind is that what we want during marine operations is the sea state at the exact position of the operation and at any moment in time. So it actually excludes some of these means. Nonetheless, if we take a look at the classical wave buoy, the estimation principle is somewhat that the buoy moves in waves. So based on the measurements of motions of the buoy, we can process these motions and get an estimate of the sea state. And to some extent, this is exactly what we would like to do with the ship. So we call it just the wave buoy analogy because the principle is exactly the same. And why is this so that we can use ships? I think especially these days and for the past 10, 20 years, ships have been installed with a number of sensors to monitor its current condition. And what we would like to make use of is exactly those, the very same sensors to make an estimate of the sea state. One very important one in this respect would be a motion response unit. We all have one in our pocket, most of us, I think. Simply a more advanced motion sensor than our mobile phone. So we have the basis for making sea state estimates using the ship as a sailing wave buoy, you can say. There are, however, some problems that we need to consider. It's slightly more complicated dealing with ships. First of all, ships have more details in their geometrical forms. Ships advance relative to the propagating waves. And the fact that ships, they are generally what we call a low-pass filter. So this leads me to my problem statement, or to the problem statement of the thesis, which I tried to answer through some, or worked on through some research questions. One, what are the available models when we would like to use the ship as a wave buoy? And what are the assumptions, complexities, and the solutions involved? And then what could be the future? Let's say if now we use the single ship, what can we make of it? So let me try to give some more details about this wave buoy analogy. This is a very conceptual diagram. So what the wave buoy represents is a combination of measurements and a theoretical model, and then we get an estimate of the sea state. During my work, I've actually worked on procedures both in the time domain and also in the frequency domain. I mentioned a little bit about the time domain procedures in my thesis, but today we'll simply not do that, so I'll focus only on the frequency domain procedures. So exactly what is the mathematical framework in this frequency domain-based approach? Well, you can say the governing equation system is based on a comparison of response spectra. So on the one side we have measurements of ship responses, motions, accelerations, what available sensors we have. And we can produce response spectra. Simply, that's the measured response spectra. On the other side, we could do similar theoretical calculations, obtain a theoretical estimate. So we end up having the estimate of the response spectra calculated simply by the filter analogy, where we have pre-calculated or theoretically known transfer functions, and we make an estimate of the wave spectrum, so it gives us, by this integral, an estimate of the response spectra. And then the principle is we would like to match the measured response spectra with the theoretically calculated response spectra. And we might need to do a bit of iteration in order to obtain an error that we are satisfied with. So if we should think a little bit about what kind of responses we should use, the measurements. I have found, international colleagues have found that typically it's a good compromise to use simultaneously a set of 3 global wave-induced responses. Thing is, we need to consider at least one of the responses to be asymmetric, because if we have a situation like this, waves coming in from the one side, and you can say you could mirror another situation where you had waves coming in from this side, then we need to be able to detect this difference. And what we can make use of here is, for example, the roll response, which is asymmetric about this longitudinal axis, the center line of the ship. So how does it look in practice? Well, we could have some measurements. In this case, we could have measurements of heave, roll, and pitch. This is the measured set of response spectra, and what we would like to compare with is the estimate exactly given by this equation then. So how would we solve this equation? It seems fairly simple. It's an integral equation, one unknown. The problem is, however, that this introduced C-state or directional wave spectra, it has as many unknowns as we discretize. So we need to apply some modeling techniques. And what I worked on in my work is 3 different approaches. One, non-parametric Bayesian approach, where we try to solve for all of the discrete spectral components. And then a parametric method, where we introduce parametrized wave spectra and we optimize on the basis of our governing equation system. And then more recently, together with some of my colleagues, we have looked at a you can say more brute kind of approach based on a spectral residual calculation. In my work, I've always considered ships with advanced speed, so they are propagating relative to the waves. These methods all consider a ship with advanced speed, but the strategy to include this advanced speed or forward speed is different. So what is basically the problem? You can say on a ship, the waves, they are counted at a period that depends on the speed of the ship. Illustrated just very basic, in basic terms of this diagram. So what we need to introduce is the Doppler shift that relates the encounter frequency and the absolute frequency. And this is actually a rather complicated problem in following C, which is illustrated right here. Because the thing is, let's say we do measure the encountered wave spectrum as we sail the ship. Then because of the Doppler shift, in following ways, when we need to map the encounter frequencies to absolute frequencies, we actually obtain 3 absolute frequencies. So this gives us the problem that when we want to transform the encounter spectrum into the absolute spectrum, we don't really know these values. So this is the basic problem that we deal with when we consider ships with advanced speed. I've applied in the methods basically 2 different strategies. 2 of the modeling procedures, they introduce directly this problem of the Doppler shift. And the last or more recent work based on spectral residual calculations simply solve the problem in the encounter domain, and then we transform afterwards to absolute domain. A few results, and this is more or less what I'll show today. I think it would be more interesting maybe to have some discussion about some of the results. So this is simply just to say I have found in many studies with full-scale data that these procedures, they work. You get an estimate which agrees with other types of estimates. And always keep in mind, no one really knows the exact truth when we are at oceans. So we can have other estimates. In this case, I compare the two procedures, the Bayesian approach, non-parametric approach, and the parametric approach, with an estimate based on the wave radar. Which one is the truth? Well, we don't know. We might start analyzing data, etc., and then get a more clear picture about which one is the best estimate. The same by comparing results from full-scale data using a smaller research vessel. Here I compare the significant wave height estimated by using the wave buoy analogy, and then with estimates provided by wave buoys. 3 wave buoys which are deployed in the same area. And what I've tried to include, it's not so easy to see here, it's probably easier from the paper, is that even the wave buoys, although they are located in the same area, their estimates vary quite a lot. This is plus minus 15% scatter around the mean value of the wave buoys. And then the final result, I've also tried to compare the ship motion based, the wave buoy analogy results with, at least in theory, the more accurate wave buoy. And also in this case, we see a good comparison. And this is more or less it. So I think I can say that, for the results, that generally the wave buoy analogy produces a reasonable result when we compare with other means. One problem, I think the parameter that often is the most difficult to estimate is the wave heading. And then we have looked into why is this actually so, and I will try to indicate the reason for this. But before that, one problem that I was also addressing in the research question is this fact that ships generally, they are wave filters. And what does it mean? I tried to study this in one of my former works. What we see here is we have simulated data, so I know what is the exact true wave spectrum. This is the dashed red line. And then based on motion simulations for using heave, roll, and pitch, I'll try to see, can I estimate this? And clearly I cannot. It seems that for the lower frequency, it's okay, and I also pick up the peak frequency, but then it rolls off, and I get a discrepancy. And there's a very well-defined answer why this is so. This is simply because of the filtering effect of a ship. Using, for example, heave, well, the heave response is simply not sensitive to waves higher than a certain frequency. And again, this is for a specific ship, so it will be relative to ship size. But generally, for heave of a ship, it is something that looks somewhat like this. So we see no significant vessel motion at the higher frequencies. But what can we do maybe to account for this fact? What happens if we try to introduce, say, the relative motion? Then we have the transfer function looking like this. And I've studied this problem then, or maybe the problem and its solution in the two papers, contribution 2 and 3 in my thesis. So actually, maybe before showing the result, what do I mean with the relative wave height? Well, it could be that we have a sensor located somewhere, say on the rail of the hull, and we look at the distance from this specific point to the sea surface, and combining with the acceleration at the specific place, doing a double integration of it, we actually get an estimate of, you can say, not only the relative motion, but we can actually track the absolute wave height. So if we introduce this sensor in the wave buoy analogy, suddenly we are able to get a much better estimate. So we can actually capture. It seems here, generally, we seem to overestimate But still, I think the important part is that now we can also estimate the higher frequencies. So this was more or less the specific studies that I wanted to introduce related to the wave buoy analogy. But as I said initially, it is really a topic that covers many disciplines. So I think there are some very important interrelated work that needs to be addressed. And this has also been started, but most of these kind of works, they deserve further work. So I'll not say so much about it, but I'll just introduce what kind of work we have been considering. You can say one thing for the frequency domain procedures is that they all rely on spectral analysis. And it brings into question the concern for stationary data. Very often there's nothing like stationary data. We need to consider data to be non-stationary in reality. But how good is it to work with the assumption of stationary data? So I will try to look at this together with colleagues in some papers, and especially we have looked closer into the effect of the aleatory uncertainty, meaning the short-term variability of a seaway. And this is exactly where it becomes interesting in relation to why we usually obtain less good results of the wave heading estimate. And then other things which are very relevant when we talk about the wave buoy analogy is the use of risk-based procedures to make statistical predictions. Keep in mind, again, the wave spectrum as such is not the interesting part. The interesting part is when we start to apply this and see how can we benefit for the marine operation we look at. Also, we need to not work with data that is faulty. So somehow we need to introduce fault diagnosis. And what about having different responses depending on the operational condition? Is it possible to select the optimum combination for certain conditions? So I'll concentrate on this study related to the aleatory uncertainty, because I think that's quite interesting, because it gives an explanation why we have the problem with the wave heading estimate. So in the study we tried to look at the aleatory uncertainty, and we were measuring like motions during a longer period. In this case it was about 30 minutes, and then we tried to do the spectral analysis in on shorter time histories. So we were considering for the whole time history a sequence of shorter periods, and then we could try to apply firstly just the response spectral analysis to look at what findings do we actually obtain. And what we see is depending on this time span we get different results. And what we would like to see, because we assume that was the measuring conditions that we believed were accurate, that it was actually quite stationary on the day, and we kept speed, we kept course under control. So in principle, no matter how short a time span we were considering, all the variances calculated from the response spectra should be exactly the same. What we see, and in fact they should be constant, what we see is that the tendency is that the longer time span, the more constant it becomes. So this is in agreement with our intuition. Then we have a problem, because what happens if we try to do a similar kind of analysis when we look at the phase angles? The phase angles are obtained from the cross-spectral analysis when we look at the cross-spectra. And the picture is not at all as nice. We have a much larger fluctuation, and even for the longer time span, the 6-minute time span, we have a lot of fluctuations. And this is a problem, because what we make use of to estimate the wave heading in the wave buoy analogy is exactly the cross spectra. So this is, you can say, the reason why the wave heading estimate is less good typically. So we have been doing actually quite recently some further studies on this, mentioned in these papers. But it's for sure there is a lot of work still needed in this to fully understand and maybe come up with a remedy to account for this problem. And then for the other works, I think I will leave it more or less just with a few citations from the work related to risk-based response predictions. It brings forward a novel concept which has the capability to increase the reliability of the provided guidance, although estimates of the on-site sea state is not necessarily accurate. So we are trying to introduce some kind of risk-based procedures where we take into account the fact that in reality, although we get an estimate of, say, the significant wave height, we should associate the estimate with some uncertainty. And then we have the problem related to faulty data. Somehow we need to introduce fault diagnosis. So as a side, usually several responses are available on today's vessels. However, faulty signals, they should be discarded from the procedure for sea state estimation. It makes good sense. Of course, the estimate is no better than the input we feed into it. And then another work has been focused on the automatic response selection and a little bit about uncertainty modeling. So it's this fact that we would like to be able to bring in exactly those responses which would, the combination of responses that would give us the best estimate. So we have introduced a local sensitivity analysis which is applied to quantify the importance of different responses for wave estimation. Yes, and I'm coming closer to the end. So if I should bring some conclusions from my work, well, as a direct answer to the research questions, you can say 3 different frequency domain-based methods have been developed for sea state estimation using measured ship responses. The fact that we introduce a linear assumption between waves and responses seems not to be such a big concern. It is shown in some of the contributions and also in other referred works. The procedures all include the effect of forward speed, and it also seems that it's actually possible to take into account the negative effect of the low pass filtering characteristics of ships. And that will be somewhat interesting because in the near future I'll actually be evaluating a PhD that introduces some of these thoughts. So that should be fun. To give maybe as a kind of evaluation of the 3 modeling procedures, I think it's not so easy to favor one from the others. They all have their own pros and cons. It goes for computational speed and estimation capabilities. So I think in order really to get a clear picture here, it would be worthwhile to do a very comprehensive benchmarking study, including my own work, but of course also international colleagues. And the reason should be simply to further address accuracy, robustness, computational efficiency, the limitation of the proposed methodologies, the level of variances because of uncertainties, etc. So somewhat like we have done in another paper, well, we can again simulate on the basis of some true known transfer function, the RAOs. In reality, we never really know the conditions, so we should somehow introduce transfer functions which are not in line with those we use for the generation, and this can be useful when we would like to study how uncertainties propagate into the system. So this also brings me to some of the further work, the not so closed ticked conclusions. I think in reality, it's fair to say nothing is stationary. So this is definitely worth to study this further. Could include time domain procedures that seems to have some capabilities to relax on this assumption. Fault detection and tolerance, again, much more work are needed in this area. And then this problem, how to automatically select the best set of responses. And this also includes how to introduce the fact that we deal with uncertainty in both the responses themselves, all the modeling. How do we do this in a mathematical, consistent framework? So just to give you my look on the future, I think it's very interesting to apply the single ship as a wave buoy. And then you might ask yourself, why is it particularly appealing to use ships as sailing wave buoys? We've already addressed this fact that the sensor instrumentation is already in place on most of today's ship. And then the other thing is, what about the number of ships? This is just a map of instant positions of the world fleet. So imagine if all of the ships were sailing wave buoys, although the single ship might not necessarily be giving the exact true, maybe some of them would. And combining all this information, I think that could be very interesting. We have started studies on this, and I have a PhD that will look further into this in the near future. Then the other hot topic of today, not in this room, I don't know, maybe some of them are into it, but machine learning, how can we apply this? This is being more and more introduced. So what I talk about is data-driven C-state estimation. What I've considered so far in all my work is you can say a model-based approach, very much relying fundamentally on the use of transfer function, the REOs. So I think as a first extension, it could be interesting to apply these data-driven methods, maybe based on vessel motion measurements and a comprehensive set of training schemes. And then the further steps would be maybe to make it even more data-driven, simply not only including motions, but all the available sensors that we could get information from on a ship. So it would include wave-induced motions, accelerations, hull girder flexure, engine and propeller data, which itself reveals information about the condition that the ship sails in. Rudder data, wind and current measurements. So a lot of potential also for future studies. And this actually brings me to the very last slide. Thank you very much to all my co-authors, of course, and especially Jürgen and Toshio Iseki. He's not here today, he's in Japan. Vivi for making the nice book. I hope you all will have one. And to Trine for assisting with the setup. Colleagues and family and friends, and of course also to my wife. So thank you.
Thank you very much, Ulrik. And as announced, we'll now have a small break. And I should just remind any opponents ex auditorio to report to me in the break. And then we'll reconvene here in 5 minutes at 2:45. The small break has ended, and we are ready to begin again. Invited the first opponent, Dr. Bas Buchner, to take the podium. And now I'll ask you to please go ahead with the discussion with the candidate.
Dear, maybe it can be slightly less loud. Dear Ulrik, ladies and gentlemen, I'm honored to be here in this famous institute, old university, and I want to congratulate you, that can be loud, with the work you have performed. You have, with your work on the sea-state estimation based on measurements of wave-induced ship oceans, you have contributed a lot to the important field. And this field is important for shipping safety, and as you mentioned, maybe also for green, or I would like to say blue shipping. You show in your work a very clear understanding of the field. You have studied and cooperated with many other people, and you do that in a very good way. But my role is not to praise you, but to be your opponent. And this does not take away what I just said, but it clarifies my role, especially to your friends and your wife, your family who are present. This is my role in the defense of, this is probably the one that I can sit somewhere else. No? I just vibrate too much. But this is my role in the defense. So I'm going to be sharp here and there, but that's not because I don't like Ulrik or his work. I'm an opponent from other small country in Europe, the Netherlands. And we both come from coastal states, and we have a long maritime tradition. And this maritime tradition and our trading is also reflected in our languages. I had to smile when I saw your thanks to your wife for her continuous support. I don't know how to pronounce it, but you would say altijd. We would say altijd. It's just one J of a difference. But when I speak to people from Denmark, I also realize you have the same problem as we do, that people in our country are living with their backs towards the sea. We are not really a maritime nation anymore. A lot of people in our country don't realize we are a maritime nation, and sometimes I hear Danish people with the same concern. So I would like to start with a quote from a former Prime Minister of the Netherlands. He was also a commander of a submarine, and he said the very important words: "For some, the coast is the end of the land. For others, it's the beginning of the world." And I'm very happy with your research. You put our faces, our sensors towards the waves, to the seas, to the endless seas. But I must say that reading all your work, sometimes I was had the same feeling. I was looking to the endless sea. It was complex. And sometimes I lost the direction. But what I did is, like you use your wave buoy analogy to come to an understanding of the waves, I'm using your part one as an understanding of your work. So I will mainly focus on part one. And then I directly start with my question. You do sea-state estimation based on measurements of wave-induced ship responses. And then I would like to ask, why? You're a naval architect or a marine engineer or maritime engineer. We are interested in the response of ships. The same applies for the crew. They want to know how the ship behaves. They're not interested in the waves. And you focus on the waves. And basically you focus on the waves at the moment that the problem is already there. So why don't you focus on wave prediction methods? For instance, by forward-looking radar or sensing techniques. I have a bookkeeper, and he says to me, bookkeeping is not important, because you're always looking in the hindsight mirror. And sometimes I feel your work as being looking forward by just looking to the hindsight mirror. What's your response?
Thank you. No?
Thank you.
I'm not sure if there's any sound. Is it okay? Okay. Thank you for your question, Buzz. I actually touched slightly on it in my own presentation. I mean,
you did.
The wave spectrum itself is worth really nothing. It's when we start to apply it. So, in order really to look beyond right now into the future, then we need to make some kind of either response predictions when we talk about safety for ships here and now, and we would like to give some guidance. So I think in the work which has been included in the thesis, this is not touched very much upon about the, you can say, the forecasting of the sea state. This is something which we would like to address also in this. I mentioned the PhD study considering the network of observation platforms like ships. So that's the one thing. And then the other thing would be where we also do work, maybe simply just use the response itself and try to see, can we, again, it depends on the type of operation we're interested in. If it's crane operations, we might be okay with having like a prediction, like say half a minute to some minutes into the future. Can we do that without wave information, just by looking at the response? And we have seen that there are some possibilities. But for the estimation of the sea state itself, I think still, although we would like also to be able to forecast both, you can say, in time and space, the sea state, generally the sea state does not change so rapidly. So if we talk about response predictions, statistically half an hour to maybe an hour ahead, also considering a ship that moves in this period, it might be okay to use it.
Can I?
And if I can, because I mean, I also mentioned it in the presentation in the beginning. I think what I've found interesting is I've had quite a few student projects in the recent years where they try to use data collected on ships, and we always end up in the same problem. When they want to do their analysis, what was the sea state when they were doing their operations? And in this case, it could be interesting to have the sea state just continuously monitored, although it might be only valid, you can say, exactly at that operation.
Chairman, am I allowed to interrupt? Yes? Okay. I don't. We have a different system in the Netherlands. Yeah, but your students, they are interested in the relation between the response and the input, so the wave. But in your methodology, you make use of the response to determine the wave input. So having the wave input based on the response does not help them to validate their methods, for instance. You say that, I agree that a lot of times when we want to compare our computational methods with what's happening at sea, we are lacking the knowledge of the waves. But in your methodology, you use a theoretical response to determine the wave. So I'm just wondering what that would add, because you need your model to make a prediction, and then in the end you use that wave again to validate your prediction model. So I'm struggling with that. I would like to have an independent wave prediction, which I can put into my simulation model, which I validate then.
If I understand you correctly, you think about it in the way that I have a set of responses, I make an estimate of the sea state, and then I use this sea state to make prediction of the same set of responses. Is this what?
No, but I ask you to justify your focus on sea state estimation, and then you say, I have students that need the sea state, and then I say, but why do they need the sea state?
That could be related to the calculation. If you want to correct data, when you want to do, for example, added wave resistance calculations, you would need information about the sea state to get the correct picture, really, of the truth.
Okay. Yeah, added resistance is not in your model already, so then I agree.
Yeah, yeah.
Yeah, if I can come back, I mean, I understand what you're saying, but on the other hand, you are focusing your research for such a long time on this topic. So, and then you refer to, okay, this will happen in the future. But it's your own decision to focus your research for such a long time on this topic. And you use words like prediction and guidance. But both prediction and guidance relate to something what is happening in the future.
Yes.
Whereas, as far as I can interpret your work, it is based on what has already happened. And I don't see the predictive strength in your methodology to come up with a prediction. So is there something, can you explain what the predictive part is in your methodology so that you can have guidance? Because your response that the waves don't change so fast, I don't think I agree. Because I see a lot of problems happening in the rising sea states.
Okay, I'm not sure, again, if I answer exactly what you're talking about, but in terms of predictions, this is exactly what we try to address in this paper. Considering the fact that we do an estimate of the wave spectrum, this is not necessarily accurate. Then we apply the estimate, it might be uncertain, and then we try to relate it to other types of responses that we also measure, and use the estimated wave spectrum from one set of responses, assume this to be valid, and apply it for prediction of other types of responses based on this kind of risk-based approach. So in this case, we were actually considering also the prediction of future responses not being identical to those being used for the estimate. And again, if I think also it's maybe not, in my view, fair to say that it's not useful to have the sea state, because I also talk about these operational windows, and when we talk about dynamic positioning systems, they need this information exactly now as it is in order to tune all the control models. So for that reason, then you can feed this in as input to the control system, as we also address in, I think it's contribution 17.
Yeah. Now I understand that was my second point, is that there are particular operations. You mentioned added resistance, which is not part of your response model. You also refer now to, in your work, to DP operations where wave feed forward or that type of things are useful. So I'm not denying that there is a use of knowing what is happening now to what is happening, but that is, you use what you have now for what is happening in response also now, dynamic positioning. But I can't see yet, and maybe you can explain it based on some of your work, that by measuring things based on an FFT, which is considering a significant period of time in the past, how that will help us to give a prediction the next 5 to 10 minutes. Whereas if I look to forward-looking radar technology, people are now with quite good reliability able to predict this 2 minutes in advance with good reliability. So I'm just trying to understand if I want to put my PhD students or my own research in this field, what should be my future methodology? Shall I proceed in your ship as a wave buoy, or are other techniques better in developing wave guidance and wave prediction response, or wave prediction and response prediction?
Yeah, I mean, I'm not really sure. They might claim it in studies that they can predict the wave system 10 minutes ahead. But, I mean, the correlation structure of the wave system itself might not necessarily give this. But what we also have addressed in, I think I can't remember the contribution, is of course the importance really to have the sea state here now, and we need to be able to forecast the future values based on trend modeling. And again, it seems that you talk very much about the, you can say, the deterministic predictions. So you would like to know exactly what will happen in, say, 5 minutes.
Now, maybe I can clarify my position. I wanted to discuss it later, but on the 2nd of January, along the Dutch coast, a large container ship lost more than 300 containers. And there's a big debate in our country what could be done. If you see this, the situation, my question is, what can we give the crew to make a decision? And I'm just wondering whether your methodology is able to help the crew to make the decision, whereas the roll motion already is a response they are interested in. So they're not interested in the waves at that moment. They see the ship already rolling. So can you imagine that? That is my struggle with. I really appreciate what you have done, but I'm just looking to the application and whether this is the most important way forward for research in the field of guidance and prediction.
But I mean, if we talk about parametric roll, we know that we have conditions where parametric roll would be likely to happen depending on speed of the vessel. So when we have this ratio between the encounter frequency and the natural roll frequency, then parametric roll would be more likely to happen. And this could be valuable to know for the crew when we have the estimate of the sea state, where if you build it into the models.
Yes, but this was not parametric roll, and now you make your life even more complex. I'm sorry, I was not intending to bring in parametric roll, but parametric roll is a non-linear response.
Synchronous roll you were talking about.
Yeah, so yes. but just resonant roll, just simple hydrodynamics.
Yes.
These people, they experience roll. And how could a system making use of ship as a wave buoy help them to make better future decisions in their operational use of their ships? Assuming that it is resonant roll motion, which is part of your ship as a wave buoy methodology.
But I mean, taking all the assumptions that we do, and generally we think if we have a good valid model for calculating the hydrodynamics of the ship, and we combine it with an accurate sea state, then, well, the prediction can't get any better than the hydrodynamic model is. But I mean, if we assume that the sea state we estimate and we combine it with a mathematical hydrodynamical model of the ship, I would say we should be in a position where we could calculate guidance for the crew. Otherwise, I'm not sure I understand exactly.
No, but I think when I was reading your material, at a certain moment I realized that a lot of the things you mentioned in the beginning, safe, green, efficient, safe has to do with the future, with making decisions.
Yes.
And I'm very much impressed by all the work you have done and the analysis you have done, but if I look to the final objective, then there is a lack of predictive capability of this methodology, and that is the point I want to make. And you are a professor at this university, you have to focus your future research. And I'm just wondering, based on that, and this is your doctoral dissertation, are you going to put a lot of effort in making this methodology better, or are there possibly other candidates which, if your objective is to develop methods for more safe and more efficient operations, that there are better candidates?
But I think it again depends on the kind of predictions that we would like to make, whether it's like statistical predictions, 10 minutes, 30 minutes into the future. I think we will not be able to do that deterministically. Then we have to rely on statistical procedures, taking into account the energy density distribution of the wave system right now as it is, and assuming that it will be valid also for a period of time forward of where we are. Combine it with a mathematical or hydrodynamical model of the vessel. Then we can do these kind of predictions. But of course it will be interesting, and this is why we are trying to set up, or we have set up the PhD study, considering this. What about having like a network of wave sensors? It should not just be like ships. It could be information being brought into the network from all available means for wave estimation. So we could like track the sea state in a grid.
No, also there I understand your point, because then you derive what the waves are at that moment in time worldwide. But still I'm wondering, one, what is the objective of that? Because you predict things where the response already at that moment is known, because you make use of the response to determine your waves. On the other hand, there are also maybe technologies like remote sensing which can do the same job. So I can imagine that your methodology helps to validate what is done with remote sensing. But in the end, again, and that is I think my main topic, is are you really achieving prediction for ship operations to make them more safe and efficient with your present development?
Well, I mean, wave systems, they would, if you are at just one position, the wave system would die out if no wind would be blowing. At a certain time there would be no more waves. So they're moving around, and what we think about here is if we could have like a grid, simply grids of points where we would know the sea state, we should be able also to track how it would mean, what it would mean having a ship sailing on a straight line. Right now we are measuring this sea state here. We know that 30 kilometers away the sea state is being measured by another ship, and I mean, what will we see in between? It will not be anything very radically different from those two estimates, I guess.
So your idea is then to couple all these ships together so that they are informing each other?
Yes.
Okay. I've once been in a plane where other planes crossing the ocean were informing each other about turbulence. So that is, but that should then be an automated system.
Exactly. Yeah. But this is what we will have a PhD project to start to work on, like in 5 months from now. Yeah. Also.
But I'll probably come back to it later in the opposition. But I still wonder whether there are not more efficient ways, but I fully support your idea of using this for direct application, for instance, dynamic positioning, or linking the waves to the added resistance, which is happening, because that is not part of the response. But that is more also a validation thing, because you experience at that moment an added resistance, and you can link it to the sea state at that moment, and that's interesting information which might help you to build up a model. But still, it does not predict what is going to happen.
No, but in terms, again, added wave resistance as a topic is not of any interest. It becomes of interest when you start to analyze the fuel bill, the emissions, because of having a hull which is not properly cleaned. And then you can ask, so it all relates to the monitoring when I talk about added wave resistance for shipping companies, simply to be sure that the vessels perform according to their models, and for them to make this analysis, they will continuously need to know the sea state where the ship operates.
Yes, but then, and then I close this topic. But for me, I would like to have methods to be given to ship owners where they say, I give advice to my ship, you should sail this route the next few hours because your wave added resistance is the lowest. And with the present methodology, you can only say things that are happened in the past. And you can make estimates, but you cannot look ahead, and you cannot look ahead in time and space. Because your ship is sailing and the time is changing.
And I agree with that, and this is why we would like to introduce the network-based approach.
Yeah. Okay. I thought I'd start with the complex question. I was just wondering, and this is an easy question for you then, is you use the wave buoy analogy. And ships have complex geometrical forms compared to wave buoys. I was just wondering, is there any advantage of having a complex geometrical form compared to having just a circular type of buoy in your accuracy?
I believe there would be, yes. I mean, knowing the modeling the hydrodynamics, in this case it would refer to the fact calculating the vessel's transfer functions.
But can you explain why? Because I have some sort of intuitive idea that by having a thing which is longer than more narrow, but can you explain that there is something in the response functions that makes it a better filter?
Well, you can say one thing also for wave buoys is not only the form, it's also the fact that they are very small compared to a large ship. So this makes them more or better to detecting also the higher frequency waves, which is why generally I think wave buoys, the classical ones, are considered the most accurate and reliable for wave estimation.
So that's a disadvantage of ship as a wave buoy. But do you see any advantages?
Yes, it is to have the sea state exactly where the ship is.
Yeah, okay. But in the filtering, I'm just wondering. I mean, you understand exactly how your methodology worked, but I thought maybe in the three methods you applied, maybe because there is a strong asymmetry between, for instance, pitch and roll, that your method is very efficient compared to other things.
I think there could be things because you have asymmetry. Also, as I introduced, just to detect from what direction the waves approach, is the starboard side, port side, we need to introduce roll, for example. But I think what I've considered here is again, also it goes a bit to the outlook, is just taking into account the motions. In the thesis I also introduce other than you can say the absolute motions, but the relative motion, vertical bending moment. But I think you would gain also valuable information by maybe feeding information that you would have from rudder motion, the engine, the propeller, that could bring further.
Okay, but it's not that you say, okay, because of the fact that you have a completely different roll response and pitch response, that the methodology to determine the wave spectrum is much more efficient than for a buoy. The buoy has the advantage of being small, but the ship doesn't have the advantage of this. No, it's not faster or more accurate.
No, I think I cannot really imagine that you should be able to make better estimates.
Okay. No, I was just wondering.
Yeah.
You introduced the topic of parametric rolling, and that brought me to the fact that if in your method you include the roll motion as one of the parameters in your wave estimate.
Yeah.
The problem is with parametric rolling is that it's a non-linear response, but it's in the wave frequency domain. What does it do with your accuracy of your wave?
Yeah, but this is also being discussed in I think more than one of the papers.
Can you show?
Sorry?
Can you show?
In my paper?
Yeah, because you refer to it and because I...
it's actually the very first one. I have this. Is this? if we take the very first contribution, there is a discussion about this, that roll is, by definition, a non-linear response, or it's heavily influenced by non-linearities. So what could we improve estimates by considering sway instead, because it has basically the same kind of properties, that it's asymmetric, and this is being discussed. Do you want?
No, I understand, but I made a note of your final comments, and also in your work you are pretty clear. Generally, the linear assumption is of no big concern. It's quite a bold statement. But whereas I think non-linearity. So, if your roll response is affected by the parametric roll, which is probably not in your model,
nope,
then there then this non-linearity has a negative effect on your accuracy. So, why such a bold statement that non-linearities are not important?
Well, it's based on findings that we have using the wave buoy analogy, even for cases, as I also report, where significant wave heights was reported also by the wave radar to be 7-10 meters. But of course, then it would be a matter, exactly as I also addressed, we need to consider the best set of available responses. So we need to combine. It's clear, maybe in conditions where you have a very severe situation, you would not rely on the roll motion. Then you would introduce other types of responses in this automatic.
So, but how would I know? I am doing a wave analysis, and I am getting results. Then the people who rely on this wave estimating should realize that this is affected by parametric rolling, and they just see a ship rolling. They don't know what the reason is why it rolls. So but what makes the difference in the methodology? Is there an automatic system that says, okay, this is parametric roll, you should not take that into account in your wave estimation?
Well, this is actually what we introduce in contribution 9. It is some of these thoughts depending on conditions here and now. Can we say which responses would maybe be better to rely on or not? And again, we should keep in mind we could make use of past information, so continuously improve the estimates. When we first have it running, we would know now we are maybe going towards a more severe situation. Say the period is increasing. We know it might be critical for the occurrence of parametric roll. Okay, then we should have in the system automatically something to detect this. And this is some of the work, the procedures we suggest in paper 9, maybe that can be useful in this context.
Yeah. Yeah, but my problem is not that I'm using it to predict parametric roll, but because it can be there and it can affect the procedure. But I understand what you're saying. Coupled to that, you have shown also the installation of wind turbines. There are some companies that are considering to do that by semi-submersible crane ships. And also in offshore oil and gas, we are still doing that. We know that semi-submersibles are sensitive also to second-order excitation. So their response is a result of first-order and second-order excitation. Can I use your methodology for predicting waves and operability for semi-submersible ships?
Personally, I've never looked at semi-submersibles. I know work has been done. Brazil have actually a pretty large community in the wave estimation, on the wave estimation topic. And I think they have addressed using semi-submersibles. And this is, I have an idea, this is actually what I'll be evaluating in a PhD, where they have smaller wave probes around.
But yeah, because I know it's not in your work, but can you, because this is not just about your work, but also about your vision about what, can you just think about it aloud for us? So, okay, what are the limitations? What are the possibilities?
again, do we talk specifically about like semi-submersible?
Yeah, semi-submersible. In a semi-submersible, I have a semi-submersible. I want to be able to have a good estimate of my response and my wave. What you mentioned, okay, some people put wave probes. Well, maybe a good idea, but...
Yeah, again, specifically about the semi-submersible, I'm not sure how good you can do estimates using it as a wave buoy. But again, I would then refer to this very interesting thing, as I see it, having a network of observation platforms. And then it might be that the single vessel we look at, well, we know we cannot estimate the sea state from this specific vessel, but maybe there would be surrounding ships.
But do you agree with me that non-linearities in the excitation, either coming from, for instance, parametric roll, which is a non-linearity in the spring system, or second-order excitation, which can also appear with ships with a relatively long natural period, that they have a negative effect on the predictive methodology as a ship as a waypoint?
Yes, I do, very much, because they they have as the main assumption that there is a linear relationship, and of course the more non-linear the response would be, the further away we come from our assumption. So yes, I agree.
But then I would like to warn you that doing the statement that generally the linear assumption is no big concern is quite a big statement if you make it in general, because then you should make that for specific ship types, because even tankers or other ships, or no, tankers, container ships show resonant parametric roll motion.
I get your point, but I think the statement should be seen in the light of this fact that we have many responses available, and then picking the best combination, then it would be okay, even in cases where you would say, right now it's a severe sea state, so we know roll is not good, but then we have other available sensors.
But in the methodology you propose in your work, do you take into account, for instance, I mean, because you refer to people that say that the roll motion is not one of the good responses to look to, but on the other hand you still use it in at least a number of your publications. We know that when the wave heights are increasing, that the roll response is reducing. So there is non-linearity. I'm really puzzled by in your work, but also this afternoon with this sort of bold statement that non-linearity doesn't play a role. Because what sort of roll response do you take into account when you start your analysis with 1 meter wave?
Okay, but then it's wrongly written or indicated by me, because I'm not saying that non-linearities would not affect, but I think what I try to indicate that it's possible to find good combinations in different conditions. Hopefully in the future we will be able to find the right combination of responses automatically. So we would leave out those responses which would be maybe more affected by non-linearities in a given situation than others.
Okay.
Yeah.
I'll probably come back to it later, but I'm just... let me have a look. In equation 2.1, and also the very interesting graph 2.2, and you just explained that also this afternoon. You have the complex situation of ships propagating in waves.
Yes.
And I know you didn't discuss it, but a very similar situation occurs when we are operating a ship in a current. And as you have shown, and I know that there are quite strong currents along the Danish coast, we want to do an operation in waves and current under different angles. Can you explain to us, to me, how your methodology would work for ship which is on one position but is considering a strong current.
I mean,
you can also use the paper if you want, but because it's
I mean, I think when we would like to calculate the hydrodynamics of the ship, well, we need to use speed through water. And then that might become a question in itself. Can we trust any speed through water measurements? But I think that's not really what you're talking about here. But I must say I've never thought about studying like extreme cases where you have wave systems on like very strong currents. This is not anything that I've considered, no.
Okay. Can you think about it aloud, maybe? I mean, we know that, for instance, the pitch motion in current is, if you have waves, head-on current and head-on waves, that the pitch motions can increase strongly.
Okay.
But the point is, I am at one location, there is current, there are waves.
Yes.
How would you change your methodology to make it work? What do you need? Do you need to make another? What is your counter frequency? What is your what sort of response do you need to take into account?
In order to have like this
ship as a wave
principle,
yeah, the principle of ship as a wave. I believe you have convinced me. I need this, but now I need it for a situation to install a wind turbine along the Dutch coast.
Okay. Yeah. I'm not so sure I have an answer for you here now. What can be done in that situation where we really have strong currents interacting with wave systems? Of course, it can create very serious situations. We know that also from some of the larger ocean areas where we have this critical scenario. But I think I would have to owe you an answer to this question because I can't answer this.
No, I don't have the answer directly either. But what you should realize, I think, at that moment is that when you're staying at one point in time, that the wave on the current is the wavelength is longer with the same wave period.
Yes.
So I think you need to calculate the response, including the current. But I think if you stay at one location, that the wave spectrum is basically measured with the underlying current. But I would recommend to take it into account because a lot of situations you have a ship sailing on current and it might affect your... and it's also nice as a sort of brain teaser, I think. I don't have the answer.
I know, and I can't remember if I mentioned it directly, but in the contribution, but then it's in another contribution which is somewhat similar to the various contribution 16. We did some further studies using this sea trial data from Trondheim, and it actually occurred that there could be quite a large influence of currents, and then I think it is actually in the other paper not being part of the thesis that we talk about. We need some further studies to analyze what this problem having like waves on a current system and especially also related to what speed should be used. Well, we know it should be speed through water, but we also know that the speed log, the Doppler velocity log is not.
But really the Doppler effect is different when you stay at one position and the current is there. But it might be interesting to study because it's quite relevant for a possible application of your work. A final thing about this nonlinearity on the response side. If we know that the raw response is reducing with increasing wave height, you choose one response, for instance, typically linearized around 2 meters significant. But the C state is higher do we get a underestimation or an overestimation of the C state?
I mean, generally, I think we cannot say that.
No?
Whether we...
But I help you already do it by saying that particularly this is happening, that the raw response is reducing by increasing wave. If that happens.
Oh, you mean, so we are in a
we assuming, is it, because I was just wondering, do we get an overestimate or an underestimate of my waves?
So, but you're saying the transfer functions that we use have been calculated for 2 meter significant wave height, and now we experience a reducing significant wave height.
Now or an increasing, 4 meters, 5 meters.
An increasing?
Yeah, increasing.
Yeah, but it means that in this case we would actually have transfer functions being, again, depending on the non-linearity, they would be smaller than expected, so we would actually overestimate. We have to take it to the other side, so we would overestimate, I think, right?
Yeah, but again, there I think I would recommend to be a bit more careful in this statement, because we are interested in waves when waves become high, when waves become steep, slamming, green water, extreme roll, and you get wave breaking, you get non-linearities. And you need to give a reliable wave for these extreme situations. So, but that's my final point. Yeah, but if you look to equation 3.1, which is the major equation in your work, it is clear that you are very dependent on the accuracy of your theoretical response. Can you tell us a bit more about, did you do any sensitivities? Did you check different methods, for instance, for shift forward speed? Did you check 3D diffraction calculations? Did you check strip theory? Did you check different kinds of models for ship propagation speed? Because I missed a bit of the sort of sensitivity in the accuracy of the response.
Yeah, but I think you're right. A lot of sensitivity studies could be made in this respect. I talked a little bit about it in one of the slides, where we actually did do something like you're saying here. Where is it? No. Something similar to what I present here, that in this case, of course, it's a simulation study, so we would exactly know what would be the correct transfer function. But what would happen if we then apply another set of transfer functions? In this case, I think the true transfer function, they have been calculated by a panel domain code, and then we would apply as RAO2 a set of calculations based on strip theory.
Yeah, but I just doubt whether there is a true REO.
Oh yeah, in reality, yeah. But this is why I suggest that we need also, like the point says, to further address accuracy, robustness, computational efficiency, the limitation of proposed methodologies, the level of variances, and this would be a natural part of sensitivity studies.
Mm-hmm. Yeah, but I think it's very important to make clear to people that the accuracy of the theoretical model is very important. The problem is that to validate that linear or that REO, normally you would say, I have the waves from the outside, I do a validation with what is happening at the sea, but that is not possible because you use your response as an input, so you will always get the perfect answer.
In case of simulation studies, yes.
Yeah, but also if you have waves measured with a wave buoy, then you can determine the accuracy of your REO, and then you can use that REO for your wave estimation based on the response.
Yeah,
I understand. Okay. Thank you very much. Yeah, you discussed already during your presentation a lot about stationarity, and it's clear that you realize that yourselves as well. I already discussed with you the fact that you're always looking backwards. But for but you still rely on this FFT approach.
No, that's not true. I also discuss it, Ali. I think generally the spectral analysis in the work we've done, sometimes it's FFT, sometimes it's some of the parametric approaches.
Yes, okay. But still, I mean, you discuss the FFT approach yourselves quite extensively and the limitations. Did you consider the sort of the wavelet type of analysis? Because we know that there is a lot of variation, and you have shown that in the phase angles.
It has been considered, yes, but not in any concrete terms. But I think that would be very interesting to look at, what we can gain from this. My colleague in Japan, we have some thoughts about doing this.
Yeah, because the wavelet analysis, of course, is considering a smaller period in time, and I've been involved in research specifically on large sea states, where you see that in large sea states, because of locking of phases in large wave groups, you see that there are changes in the wave spectrum because of nonlinear interactions, which completely affect what you are doing.
Yeah.
Okay, but you didn't...
we haven't looked further into it.
Yeah, because I think you stated correctly that nothing is stationary. No. And I think, but that is also, I think, still one of the limitations of your methodology. I mean, you assume linearity, constant speed and course, stationary and ergodic process. I think you have to assume constant water depth, constant loading condition, constant control settings.
Yes, that would probably be at least, like, for the formalities, the correct way to do it. Yeah. But again, I can just refer to concrete practical studies of full-scale data when we start comparing this approach with other means, the wave radar, wave buoys. It's not so easy to say one is very much better than the other. So,
no. You have worked with people like Professor Junge Jensen on, and he is specialized in extreme events as well, fatigue, FX. But I mean, I have been working myself on green water. Did you find anything? And I'm coming to the sort of the outlook part of your dissertation. Did you find any indication in your methodology where you can use your wave estimates also for the predictions of extremes? Because, I mean, in the end, you put this whole sea surface back to a 3D spectrum, which is very smart. But in the end, I'm not interested in that spectrum, but I'm interested in extreme response and extreme distributions. Is there anything in your work where you say, okay, you see, if this is happening, then I should, because I'm looking again to the sort of prediction.
Well, I mean, you could, of course, you can apply a given wave spectrum, whether you consider it as extreme or not, for making extreme calculations or extreme value calculations related to roll. For example, we have had a fairly recent PhD project about evaluating extreme values of roll-related problems. Mm-hmm. So in that way, you would again naturally feed in the current information you would have about the sea state and do the kind of analysis which would be required. But
no, but I understand. I mean, it's already quite an achievement to come up with a wave spectrum which is not a long-crested wave only. With it can be double peak spectrum. It's short-crested. So, but I'm just wondering. People are not interested in averages. People are interested in extremes because they cause the problem. So I was just wondering whether in your research you found specific indicators in spectra which result in extreme events. Or
no, I think there would still be again further study needed really to enlighten this. But I can say some of the procedures, they are non-parametric, so you would be able to consider the fact that you could have cross-coupled single wave systems.
Yeah. Coming towards the outlook as well. You have mentioned the methodologies like machine learning, artificial intelligence. We have discussed equation 3.1. You are a model-driven guy. I see nowadays a lot of, like I think 95% of us being in the naval architecture side. In my own institute, I see a few of these guys who are daring to go into artificial intelligence, image processing, machine learning, all these terminology. I don't understand all the differences. My own feeling is, okay, yeah, but they don't know what they're doing. We are the guys from the model, we understand it, but there is a lot of uncertainty in your methodology based on models as well. Yes. Can you first explain to us in a bit more detail what you understand from data science and give us a review of the strengths and weaknesses of both methodologies?
I'm not an expert in data science either, but maybe we'll get at least I'll get more experience in some future work, because as I also suggest here, I think it will be very interesting to look at different ways of making use. Either it could be, as I maybe see as a first kind of extension, to have data-driven approaches taking into account recorded motions, comparing to a lot of trained data where we know the exact wave conditions.
But at some, I mean, because neural networks are in the market already for some time, you made for some reason a decision to proceed with mainly model-driven. You were never sort of teased to say, okay, I'm going to try this. I want to understand what's happening. Because I understand what you're saying, but for some reason, you and many others, myself included, we sort of try to stick on the path we know. Whereas that can be a very, it cannot lead to the future. Maybe we are missing things. So are you? I
think I would turn it the other way around. At least now I'm realizing it could be interesting. But maybe I should have done that like 10 years ago. But
what sort of strength do you see of a data-driven approach?
Yeah, but I know, I talk to Maersk guys, and I know how much data they have in their possession. And I really see potential in looking, that's the last point of there, to include all the kind of...
But that's too easy, I understand that, but that's what I can say as well. But imagine that you have the same information, so just ship response data, and the problem with data science, with machine learning, is that we are making it very big, but let's make it small. Just, you have the same information.
I mean, this whole thing about data-driven approaches, you can say to some extent it doesn't get any better than the training allows for. So if you make poor training, then...
Yeah, but your method is not getting better than the training of a model.
No.
And it can be very smart in training. I mean, I see the guys working in imaging and image processing. They do things I cannot imagine. Whereas I understand, because I'm from that field, I know the limitations of responses.
Yes.
So, do you see advantages of data-driven methodology, or you say no? In the end, the physics are the most dominant thing.
I think at least until we have a clear understanding, you would not throw away the model-based approach. But there might be a path around that could lead to better estimate by purely data-driven approach. But I don't know. We haven't looked into it yet. But we also indicate this in the thesis. This in the end. What about image recognition? Could it be interesting to look at?
Yeah. No, because I mean, I'm not sure how it is here in Denmark, but I know that most of the students that come to us, they are very good sailors. they are already good sailors before they know the models of hydrodynamics of sailing ships. So we learn not by understanding the model, but we learn on experience. So maybe data-driven methodologies are quite good, although they don't understand it exactly. Yes. Okay, my final point is you are looking forward to a very good career here. We have discussed your model-driven approach. We have discussed machine learning, remote sensing, forward-looking radar. We did not even discuss mid-ocean modeling. I mean, why, if you want to know waves, just start to study the wind and the wind waves models, and that's maybe much more effective. If you have to choose, and your objective is to make ships more, let me quote yourselves, safe, green and efficient, and you have limited budget, what will be your choice, apart from the fact that this is fun?
Yeah, but again, I can refer to, as I also indicated in the outlook, I think it will be interesting to merge the available information we already have from the huge fleet of ships, combine it with, for validation purposes, satellite measurements, to update our network-based approach using satellite data or buoy data, and having all these ships sailing.
Yeah, you find it difficult to choose, but now the proposal said you get 1 million euros, or how that's, I think 8 million kroner, but it should be one of them to do your research. I mean, what I see in your work, also if you look to your 3 methods, you don't think it's interesting or relevant to make a decision, but sometimes I think you have to make decisions. So you have done all this work, and you have the possibility, maybe we miss one of them. What is the most promising method in your view? If you are allowed to have 4 PhD students and you're not allowed to distribute them over the 4 topics.
So you asked specifically about the 3 methods?
No. I just noted that, and maybe Professor Inchik will discuss that with you later. But that's another where I noted that you have a difficulty in making clear. Say, okay, you make sometimes clear statements, but then you say that this is so. The 3 methods, that's fine. I leave it to others. But now I talk about if your objective is to have safe, green, efficient shipping, you want to do that with some sort of methodology. There is budget for a number of PhD students. What would be the method of your choice?
But I think, again, I'm not sure if I understand, but what we need here is some careful comparative studies of these methods.
Yeah, but
which has not really been done yet.
No, but I'm not referring now to the 3 methods, because that is part of your work. I won't discuss. Maybe Professor Inchik will do. But if I go back to the beginning, the why. The why, I understand, is you want to give designers, you want to give operational people, you want to give them advice, decision support.
Yes.
I'm stepping on board of this big container ship. The container ship is moving northwards along the Dutch coast. They have to make a decision. Are we taking the short route to Bremen along the Dutch coast, or we take another route? We just sail around. We go further north. That is what you want. And then I say you have money to help these people in the future. You can proceed with your present work. You can go for machine learning, remote sensing, forward-looking radar, mid-ocean modeling. And there is money for the research. You're allowed to go on for 10, 15 years with this topic as well. What would be your choice?
But I think I've indicated this. I think it would be very interesting to consider many ships, many different platforms, merge all the data to really be sure that you have reliable estimates, not just at one point, but including weights from other types of estimates coming in from ships at other positions. Satellite data coming in, very backdated, 6 hours, but it could be used for calibrating the larger network-based approach.
Okay. So you say that apart from the things I mentioned, you still say my network-based approach is the best way to make ships more green, smart, and efficient.
No, I'm not saying that, but I'm saying it could be interesting to study.
No, that's an interesting, but there's a lot of things are interesting to study. But we started with the why, and you also started with a clear statement that your work is important to make ships more safe, green, and efficient. And that, if that is the objective, then I ask you, okay, you're working for a university, I'm working for a simple applied research institute. We spend only money on things that can help us the next few years. But I mean, we need your input, your methodology development for the next 10, 15 years. And that means that we need students on the right topics. And then, but your answer then is, if I have money, I have PhD students, my topic of choice is network-based wave, ship as a wave.
And together with the study of machine learning procedures.
Okay.
I'm not so sure what you are addressing.
No, but maybe that we can leave that apart from the discussion. Thank you very much.
Okay.
Thank you, Mr. Chairman. I'm satisfied with the response of the candidate.
Thank you, Dr. Lars Buchner. I'll now invite the second opponent to the podium, Professor Attila Ingegic from Strathclyde, to continue the opposition of the candidate.
Thank you very much, Rector Larsen. Good afternoon, colleagues, ladies and gentlemen. I'm also very honored to be here this afternoon. And first of all, I'd like to thank Ulrik for his very clear presentation and also putting together a very nice dissertation. And there are various, obviously during the discussions with the first opponent, many topics are covered. So I will catch up in certain areas. Some of them might overlap a little bit, but at least we can have maybe some sort of confirmation in some of the areas. So, I mean, this, of course, aspect of linearity assumption has been discussed thoroughly, during the first part. Now, my question is, again, just to wrap up, if you like, the accuracy of your methodology, how much this depends on the ship size and ship's shape, and also against, wave particulars. So if I am to use your methodology, equip my vessel, and also cover as wider spectrum as possible in terms of, sea states, what kind of vessel in terms of size and also shape that I should go for?
I think the very short answer, if we would like to use a ship as wave, the smaller the better. But of course, we don't have that in our position. But the fact that ships, they do filter waves, so somehow I think you would need again to carefully pre-calculate transfer functions of the specific vessel, and in this way have a feeling. So I cannot generally say what type of ship. I think you would need to study what type of ship are you thinking about using for wave spectrum estimation, and not before you have that, then you can start doing this kind of sensitivity analysis, as we have also talked about previously.
Sure, but in order to eliminate some of the non-linearity effects, do you think would it be not better to go to a large size like tanker form or barge form vessel?
Exactly, that's it. And I had a reference on one of the last pages. Again, I can't stop referring, and it's not on purpose, to this network-based approach. That it's not so simple just to say that the smaller ship always is better. Because in that study we actually found that for the lower frequency range, actually the larger size ships are better. And that would be the same, you can say, as you indicate, in more severe wave situations where you would know now non-linearities will start to really influence on the smaller sized vessel.
Indeed. So, and you obviously, in collaboration with your partners like Professor Iseki in Tokyo, etc., because they use different ships and you use different ships, and how did they come up? I mean, were there any sensitivity analysis in terms of how the vessels behaved and how the results compare with buoy-based measurements?
I think in specifically referring to Professor Iseki, most of his work is actually based on their own training vessel, which is a relatively small-sized vessel. So usually they don't see those very negative effects of filtering, but of course it also depends on the wave condition. Again, in very severe situations, there might be heavily influenced from non-linearities. And in my own case, we still, as I also indicate, we need some careful studies to address the influence of non-linearities, the wave filtering effect. So I cannot give you like a specific or concrete answer.
Okay. How many ships are now equipped with these devices that you continue taking measurements and developing spectrum?
But, I mean, the wave buoy analogy as such, to my knowledge, is not really developed in a commercial scale yet. So most of the work that I see also from international colleagues is based on like ad hoc analysis.
That's what,
and this is why I think also, as I introduced today in the introduction, that it could be fun to make it more like practical. So to have it in somehow commercially scaled and really to get a better feeling of how does it behave, not just in some post hoc analysis, but from a day-to-day operation on container ships.
Yeah, I mean, that's what I was going to, follow up my question to that was going to be, obviously you develop this technique, and, are there any companies like Maersk, for example, taking this up and apply or going to equip their ships to generate this network of vessels to gather data and produce a new...
They are very much concerned about business cases, so if I can show them somewhat similar to Bas talked about, 6 months from now, by doing this, then I'm quite sure they would be... but this is research, and this is very often what we are struggling with, that I can't promise anything, but they have shown interest in this thing. But what we are also talking about is what kind of responses should we use from the ships? Should we install motion reference units on all the ships? Or so there are still things that need to be addressed. But I mean, speaking about sensor installations, and most of them, they are very heavily equipped with sensors. I think really to gain a good, solid analysis by using the wave buoy analogy on in-service operating ship, we will also need information about the motions. And again, many ships they do not necessarily have the motion sensors on board.
No. Okay, we may come back to this later on during the wrap-up part of our discussion. But let me move again. This was touched upon by Bas a little earlier. But the effect of current, coming from different directions, obviously, there will be different regions with strong currents, and some of them will be opposing to the waves, and so on and so forth. How this is then going to actually change the methodology, and how this is going to affect your analysis?
I think, as I replied to Bas, I haven't thought about including current so far.
Sure.
Mostly we have looked at ships operating like on larger parts of the oceans where
Sure.
the ocean current not necessarily is influencing too much. But the thing is, of course, we never really know. Maybe the current was influencing because we don't have any. I've never combined a sea state estimation study with studies about the reliability of the velocity, the speed through water log, including the speed over ground, which you would need in order really to have a clear picture of the current, and again assuming that the speed through water log is trustworthy.
I mean, if current values are known in certain areas that you take to measurements, do you think it's a good idea to correct the spectrum, due to the effect of current? Because there are techniques that one can do that. Can we not?
I think if you have correct information about the current, you should somehow introduce this into the estimate.
Yes.
And then again, I have to owe you an answer on that because it's not anything that I've looked into.
Yeah, fair enough. That's okay. Thank you. The other question that I was going to ask was the techniques that you develop, would they actually take into account the locally generated waves and swells?
What do you mean there?
Well, I mean, if you are doing the spectral analysis, etc., but then you are measuring the responses of the ship.
Yes.
But some of those may not be. Some of the responses may not be affected. Let's say swells coming, because this is going to be swell, and may not be picked up by your measurements. And how will that then affect the spectral analysis?
But then I think it again becomes a matter about the ship being a filter, in essence. I mean, if the ship doesn't sense any waves, well, we can use it as a wave buoy.
So then would the spectra doesn't need to be corrected if swell coming from one direction?
No, because generally, I mean, swells will affect a ship, which is actually not the case with wave radars, assuming that we have a situation where you just have a pure swell. But if you see a response in the ship, then you would pick up the swell component as well, although there would be no wind. Yes.
So you are I thought you are only measuring heave, pitch, and roll, but you are also measuring sway?
Yes, we also have studies where we have used sway, and this contribution one that I also talked to Bas about, that I do a discussion and I try to compare estimating the sea state using sway, heave, roll, and heave, roll, pitch.
Okay.
And in that study, there was no clear picture whether the one should be preferable to the other.
Okay. In your transfer function estimates, what kind of technique did you use?
Well, it depends.
Yeah.
It's very often, I've also been so fortunate that if we have had data from an external provider, they have also provided the transfer functions. And it has varied. Sometimes it's panel domain based codes, and sometimes we have calculated just by our in-house strip theory code. And again, I think, and this is also confirmed by other, especially Professor Iseki, that I think very often there are so many other uncertainties influencing the whole thing that maybe it is not so crucial whether one would use like a panel domain based code or strip theory codes. Of course, you can say generally the more correct, assuming that we can measure what is correct, the better the transfer functions are in terms of accuracy, the more likely we are to make a correct estimate.
Then I was actually going to ask you, yourself or Professor Iseki or some of your other collaborators, have carried out any sensitivity studies to see what happens if you use, for example, panel method versus strip theory, or 2D panel versus 3D panel method, and so on.
Yeah, and I think I had this. Then this, you can say, this is for simulated data.
Yeah.
But this, I guess, is something what you refer to, but it should be for full-scale data.
Yeah.
And I think there are none of the contributions that include this kind of no. But as far as I remember, we have done some of these types of analysis.
And then
but clearly, again, it would be interesting to do a lot more.
Sure. Now, following on from that, you've done a lot of analysis, obviously, to estimate C spectra. And then, when you look at the various spectral formulations, Pearson Moscowitz, in the North Sea, John Swab, etc.
Yeah.
For a given sea state, have you actually done any correlations to see how good they are?
No, but that's also an interesting future study. Actually, we had a review done on one of our recent papers where the reviewer was saying that the use of the Brett-Snyder spectrum was, we couldn't do that.
Sure.
It was validated by many people that it was not useful anymore.
Sure.
The case was we were looking at a simulation study, so for that specific reason we could use any type, but I think it could be interesting to look more into it.
Yes.
But coming to specifically Brett-Snyder, it's interesting that the IMO actually recommend the Brett-Snyder.
Yes, exactly. Yeah, I think that will be very useful contribution from your work for practical use, and maybe that will be next student's MSc thesis or something.
Exactly.
Yeah. Okay. Following on from the same trend, and obviously, Bas again was discussing with you, different techniques in terms of radar measurements and satellites and so on. Again, was there any correlation? I know you've done always correlations between buoy measurements and ship motions, but have you at all looked at the radar and the satellite type?
Yes. Contribution 1 considers, I think, only like comparisons between the wave buoy analogy and radar measurements.
Sure.
And from this set of comparisons, it's not so easy to say whether the one is better than the others, because if we include satellite data, which are doing that study, then they seem to be capable in both approaches, the wave radar and the ship motion-based results seems to be agree fairly well with the satellite data. I have a larger study done in contribution. Is it 9? No, not 9. Where we do, where I analyze sea trial data. It's it's contribution 7.
Yes.
Where we have included, this is based on sea trial data from a smaller research vessel in DRDC Atlantic in Canada, and it was a very extensive study where I compare wave radar measurements, the ship as a wave buoy, and the buoy measurements, and in that case, actually, there was a small favor towards the wave buoy analogy if we were comparing with the classical wave buoys. But then again, are they giving the truth? That's always difficult, because we could see even for 3 buoys located within a quite small area, the buoys, they were not measuring the same, and then it comes back to this about the short-term variability of the sea state in itself becomes important. Okay. So I think, as I also try to indicate, wave radar is is a useful means for wave estimation. Some people rely heavily on it, and other people, they don't trust it so much because you need very, very careful calibration. And this was exactly what they suffered from at DRTC Atlantic, that they would like to use the wave router, but they realized that in terms of the significant wave height, it very often gave incorrect results because it was poorly calibrated.
I mean, okay, but that's very helpful. Thank you. Now, just thinking again, you know, maybe this is kind of loud thinking together with you. And, you know, nowadays, of course, the satellite navigation is very advanced. So, you know, wherever we drive, you know, we use satellite navigators and they tell us the optimum routes and so on and so forth. So do you think one day, actually, ship seafarers will just actually switch on their satellite navigators and then decide what will be the best route to go to, rather than worrying about all these stuff that we have been discussing all this afternoon?
I mean, we never know what happens in terms of computational power and data processing. So maybe one day we can actually have real-time estimates from the satellite.
That's what
I think it is still some time ahead from us, but I'm not saying no, that could happen.
So coming back to, you know, Bas's question, if you are given X million of, you know, euros or Danish kronas or whatever, so would you put your money into that area then?
I think, taking the fact that ships already are installed with a lot of sensors, I would put my money there and then introduce the thought about, can we merge all the information we have from the many vessels?
I know you're so passionate.
We also have the satellites to provide validation data.
Sure. I know you are so patient with your topic, and I don't blame you with that answer.
I have to be today.
Okay. Now, if, you know, I ask you, you know, you have done tremendous work over the last so many years, you know, and one thing that, you know, will make you feel so proud in your thesis or in your studies, in your publications, what would that be?
If I should point to like one thing?
Or if you like more things, but it is, you know, a couple of things maybe. That, you know, you say, look, you know, this is what I have done. This is really now opening up, you know, future research areas for the next generation to, you know, also benefit and take further. I will, of course, also work in this area.
I'm not sure I can point to one or two things,
sure.
But I think it's more the combined effect of these studies that, in my view, it shows that there are some potentials for making good use of ship motion data or other types of ship response data. And whether I can, no, not like exactly one thing, it's the combination of it all. Also because it is such a diverse area. It includes so many disciplines, as I indicated in the introduction. It's classical naval architecture, because we need to know information about the ship. How does it look? What should we expect from the transfer functions? Then we go into seakeeping. Then we take in measurements, time series analysis. So it really includes a lot of different things, which I think also is the fun part.
Okay. So one thing that I was wondering about, obviously uncertainty analysis, you talked about it, of course this is you know, quite a large area, but how confident are you in the accuracy of the measurement devices like accelerometers, the strain gauges, and or the load sensors or whatever you are using on board the ship? What are the sort of error bands?
Yeah, but in the studies I've done, they're taken, the measurements, they are to some extent taken for certain.
Sure.
And this is why in contribution, I can't remember them from each other, 8, that we talk about fault diagnosis, because of course we can never like or we cannot be in a position where we always trust the set of measures. So we should somehow introduce fault diagnosis in the system. So all this, the sensors, they would be evaluated even before. And now I'm not just talking about having the optimum combination, but we should be able to detect faults automatically.
So, I mean, you know, if you were doing the same measurements you are doing today, 10 years ago, do you think, you know, really you have more trust in the sensors and in the measuring devices, or?
That's not so
your
much.
Area.
No, I don't know.
It's not your area, but it's
no.
Yeah.
And I wouldn't be able to say. No.
No. Okay. Because, you know, I mean, it's when some years ago I was doing some experiments myself, you know, some devices were very sensitive to, for example, you know, temperature changes, etc., whereas, you know, some devices were much more robust for, you know, certain temperature changes or whatever, you know, that kind of thing that, you know, I wonder whether you...
But this is actually, this is some of the things that we indicate in this contribution, that we know that sensors, they'll be installed, and sometimes Hall vibration might affect the sensor, so we should be able to detect this if it's a problem to the sensor. But again, I can't say what level of accuracy the sensor should have for it to be useful.
I think that regards some sensitivity analysis.
So I think it could be interesting one time to have like the best on the market sensor available for motion measurements. Then go to the captain and put my mobile phone, have it to collect data and analyze the data. See, can I get as good estimate using the data from my mobile phone? Of course, I need to know exactly where I put it in order to calculate the transfer function for that specific point. But I think that could be fun to do.
Sure. You know, when I was a student many years ago, we were using World Wave Atlas produced by Hoppen. You know, they converted into CD form and so on and so forth.
Yes.
Do you think it's time now to modify or to revise that data?
I think the more data that's coming in from platforms generally, I guess it would be useful to have a look at that and see, does it really reflect what we are measuring now?
But you didn't have a chance to do that?
No, I haven't done it. No.
We have asked you a lot of questions, and I think it's time now to stop. And once again, thank you very much indeed for, you know, answering all our questions. And
try my best.
Thank you. Thank you, Mr. Chairman.
Thank you.
So this means that the assessment committee have exhausted their questions to the candidates. I have not been notified by any in the auditorium that they want to ask supplementary questions, and that means that we are at the end of this doctoral thesis defense. And let me just before finally closing explain what is going to happen now. So the assessment committee will have a private meeting and decide on what to recommend to the academic council. If the decision is to award the degree to the candidate, if it's unanimous, then that decision is final. Otherwise, it will be up to the academic council to decide what is going to happen. But what I can do now is that I can congratulate the candidate on taking part in a presentation and a discussion of his work, which I will do now. And at the same time, give you this bouquet of flowers. Congratulations to that. And then I would just like to invite everybody to join us for a drink and a snack just outside the auditorium. Thank you very much.